Okay, multiple regression analysis. We're going to first revisit the online sales example. So we have these following observations that show the amount of time spent in minutes using a support chat feature and their corresponding online sales in Canadian dollars for 5 customers. So we conducted a correlation and regression analysis, and we found that the time spent using the chat feature was in fact statistically significant in predicting online sales. So that's very useful, say for a company. That would be very important to know that. What if we have, though, more information about these customers, not just the time spent in minutes using the chat feature? Let's say, suppose we know their heights. Well, it might be statistically significant in predicting online sales, but in this case, it also might not be practical significance. Same thing, say, with eye color or their shoe size. They might not have any practical significance. But what if we have something that did have practical significance? So you can think about what type of variables would be possibly used in predicting online sales. What sort of information could we know about these customers that might be useful? So what if we have, say, their age? So age could have an effect here. It could be useful in predicting online sales and be statistically significant, and also be practical if, depending on, say, what the product is. Also, we have time spent. Suppose, younger people might spend more time on the chat feature, be more comfortable, and so on and so forth. So a lot of different reasons there could be a relationship between age and time spent and online sales. And so if we were to use the time spent using the chat feature as a predictor, plus the age of the customers, we would then have 2 predictors. And when you have more than one predictor, we have then a multiple regression model. So let's take a look at what that looks like. Here is the multiple regression model, where y is our response variable, and it is equal to beta naught, that's our constant in this case, plus beta 1 times x1, which would be our time spent, and then add that to beta 2 coefficient times x2, which would be the age of each customer, plus we know that there would be some error associated with the model, that's our epsilon. So this is the true model, and we estimate it using calculus, minimization and maximization techniques in calculus to come up with the multiple regression equation. So y hat is used to estimate y, and y hat is a function of b naught. So b naught is the constant that estimates beta naught. Right there, it estimates beta naught. B1 is the coefficient, the regression coefficient that estimates beta 1. So B1 estimates beta 1. And X1, that would be, in our case, time spent. Then we'd have B2. It's used to estimate the coefficient beta 2. And X2 would be our age. So that would be our multiple regression equation. And then you would build the model to see if they are statistically significant in predicting online sales. So here's how we evaluate that. So you can test the overall model to see how good it is. So you have your null hypothesis where all the coefficients, right, are equal to 0, versus the alternative hypothesis where at least one of the regression coefficients does not equal 0. We can also test for individual regression coefficients. So we could have this one here. So these are each individual test. So the null hypothesis would be the coefficient beta 1 is equal to 0 versus it does not equal 0. And then we could have beta 2, that's another test. So the null hypothesis is beta 2 equals 0 versus it does not equal 0, and so on and so forth, depending on how many predictors you have. So K in this case is the number of predictors in your multiple regression model. So let's take a look at the individual tests first. So the individual tests here, so you have your test 1, this would be test 1 for the coefficient beta 1, and test 2 would be for the coefficient, we sometimes call them the regression coefficients beta 2, and the test statistic right here would be t equals B1. So if we're doing the first test, this would be the coefficient B1 that estimates for beta 1 divided by the standard error for B1. And that comes out on the computer output. It needs to be given to you. And here is the confidence interval for beta 1. So it would be B1 plus or minus our critical value t times the standard error for B1. Okay, so that is a way of finding out if both of those, so the t-test and the confidence interval, are ways, just like in the simple linear regression, these are ways to test to see if the predictor, so in this case time spent, is statistically significant in predicting online sales, even if we have age. So even though we found it's statistically significant by itself, it may no longer be statistically significant if age is added to the model. So you have to actually retest it. Okay, and we would also test for the time spent on the chat feature and also the age. Testing the overall model, we've seen this before too, very similar. We have the regression source, the residuals, so the sum of the squares for the regression and the sum of the squares for the error. K is the number of predictors, which correspond to the degrees of freedom. And then for the residuals, it's n subtract k minus 1. We can also write that as n subtract k plus 1. So that's the degrees of freedom for the residual sum of squares. And then when you take SSR divide by k, you get the mean square for the regression. And if you take SSE and divide by the degrees of freedom, you get mean square error. When you take the mean square error, actually the mean square of regression, divide by the mean square error as written here, you get the F value. The F value can also be written like that, like we just mentioned. And it can also be written in terms of R squared and the degrees of freedom. And then of course we have our total sum of squares. And this is a way to test. You then look at the F value, compare it to the table value, the critical value on the table, and then if it is great, if the F value is greater than the table value, then you reject. And then that means the model, the overall model is good based on, don't forget what we're testing here, you would then reject the null hypothesis and know that at least one of the regression coefficients does not equal 0, which means that the corresponding predictor variable is statistically significant. All right, we can also look at the standard error of the estimate. The expression under the radicand there, the SSE divided by the degrees of freedom, we know that that is equal to the mean square error. And so sometimes we call this SE the standard error. We also call it the root mean square error, okay, because it's equivalent. And that tells us it's a single number that tells us how good the error is in the model. Remember how residuals, a residual formula is y subtract y hat, which is the observed subtract the predicted value for the response. And that goes into the formula for the sum of the squares for the error. So this is a way to capture the entire error of the model. All right, and we also have, bring that up, there we go, the multiple determination. So the coefficient of multiple determination we know is the SSR, so the sum of the squares for the regression divided by the total sum of the squares. And we have some points that go with it. So it's very important to check these over. These are the properties for R squared, and I'll leave that with you to read. We just need to be careful. If you add, the more predictors we add to a model, the R squared, because of the formula, will increase. So one way to get around this, to make it so that we are truly assessing the model fairly, is to use what is called the adjusted R squared. So the adjusted R squared takes into consideration both the additional information each new variable brings to the regression model and the changed degrees of freedom of regression. Okay, so that's 1 subtract the sum of the squares for the error divided by the degrees of freedom, divided by the total sum of the squares for the variation, divided by n minus 1. All right, so we will look at the example and we'll build a multiple regression model. And this time though, instead of 5 customers, we're going to look at 26 customers. Makes the model a lot more interesting. So we'll look at that in the next video.